Yeah, welcome to the class. Welcome to this OS lectures, and this is the second class. Okay, and yeah, first of all, you have any questions or any queries? Because in the last class, just we the introduced the basics. We are in the basics still, but something like very briefly, we discussed about the different components of a computer at a very gross level, and then how they interact, basically how the IO devices will interact with the computer and all using the interrupts. So those things we discussed very briefly, and today we'll continue from that. And we'll try to cover this introduction maybe today's two lectures as well, maybe the even the next week also we'll continue that. So with that, we'll complete the introductory stuff related to these operating systems, and then we move on to the specific topics related to the process management, memory management, and so on. So that was the plan, and so today we'll continue the lecture, like the one which you stopped earlier and all. Okay, and another thing is that today at 11:45, I have scheduled the mock quiz. And as I mentioned, that this quiz is just to know about get to know about how the test looks like, and you also get familiarized with giving the test in the online manner and all. So might be you have done already, you have experienced in the last semester as well. But and another thing is that since the class strength is not stabilized, and that too I had taken very first class, so that is another reason for keeping this test as a mock test and all. So that way, this test is not considered for grading purpose, but still I recommend you that please take the test, don't miss it. You'll get a feel for that, and in the test, whatever the mistakes you do, so that you can able to take care in the next test and all. So that is one of the reasons for that. So please, all of you, please take the test. While taking the test, don't leave the meeting and all. So you please take the test through the Teams only in the meeting by attending the meeting and all. So whatever the announcements were made, so that you can able to listen to those announcements and all. Like the last the due time when you are supposed to submit, so those things and all. So that therefore, while taking the test, be in the meeting. Don't leave from the this general channel and all. And already the test was posted, but anyway, it will open. You can able to open it. You can able to answer that only from 11:45. So I have given a 15 minutes time and all, but as such, this test will not take much time, maybe 10 minutes maximum. Okay. So that's all about the mock test and all. So let us move on to the class lecture. And as I mentioned that since it's a 2 hours class, we'll take a break in between for 5 minutes. So let me stop the lecture at a logical end point, so that we can start the next one later on. We'll take a break of 5 minutes. Okay, so let me start. If you don't have queries, so let me go to the presentation slides.
Uh, Excuse me, sir.
Yeah, yeah, please.
Sir, in one of the previous slides, you mentioned that, like, it is mentioned that the one program running at all times in the computer is the kernel. So, what exactly do we mean by a kernel?
No, no, it's not running means actually mean to say is that most of the times it used to like executed by the CPU and all. That's what I mean. The kernel is nothing but the programs, all the programs where that used to manage the resources like IO devices and hardware, whatever. So all of them. So it used to have like managing or providing interface, provide and like connecting that for the given program, given process and all. For that purpose, like as and when today in the class today, we'll take an example and then you can able to see that for running a program, one simple program, just for copying a file, for example, you can come across that actually how many times that operating system need to be called, or you can say that the kernel routines used to be called very frequently and all. Just for simple command like copying a file from one file to other file. So you can able to see that actually how many system calls. System calls are nothing but operating system codes, operating system programs and all. So how many times that used to be called. So with that, we can get some idea about so when you're running a program, normal user program or any application program and all, so like at what frequency or at how frequently the operating system will be utilized for running the application program. So in that context, I mentioned that all the time and all. It's not that all the time means it's not the entire time and all. It's like most frequently you can come across the operating system routines. That's what I mean by that. Okay.
Okay, sir.
Yeah, right. Okay. Yeah, next we move on to these things. Like, yeah, in the last class we discussed about these things. I'm not going to the details of that again. Yeah, this we had discussed like how these various peripherals will interact with the CPU and all. Like whenever whatever the task that was given to this peripheral when it is completed, how they interact with the CPU. So it way by using the interrupt. That's what we have mentioned like because CPU is executing some program and the IO is the IO devices, some data transmission, data transfer will takes place from IO device to the device controller and so on. That way it's happening, may happen parallelly, simultaneously. So in that case, when the like for example, whatever the IO device task that is completed, at that time it has to inform to the CPU. So in that case, it makes use of the interrupt and all. So then how it then after that how the CPU will react to that. So these things we have discussed about that because and another thing is that there are several IO devices will be there. So in that case, how the CPU will know that actually which IO device has interrupted and all. So for that purpose, we have different ways to do that. One way is that using interrupt vector. So, so whenever the device is interrupted, then the CPU will send, after that, it will send an acknowledgement. And then upon receiving the acknowledgement, the device will put the interrupt vector number. That means that particular device number or whatever. So then the CPU will see that, and that is the nothing but the interrupt vector and all. Like suppose, for example, you have some 100 devices are there. So the device will be numbered like in unique way, like 1, 2, 3, and so on. So suppose device 53 has interrupted, has sent an interrupt and all. So then the CPU, when after that it sends acknowledgement, interrupt acknowledgement through a bus, and upon receiving the acknowledgement against to that immediately that particular device which has interrupted, it will just put its number like device number and all. So that is nothing but your interrupt vector, and with that, the CPU will realize that the device 53 has interrupted and it has to provide the service to that. So that way, the interrupt vector is again indexed to the a table in the kernel, like where there are, as I mentioned, suppose there are 100 devices are there. Each device has its own way to be serviced. So therefore, for servicing the each device, there is a separate kernel routine or like IO routine, IO service routine will be there. So all these things will be put it in a tabular format table, and this table was indexed by this interrupt number. So that way, so whichever the device has interrupted, then then by using interrupt vector, the CPU will come to know that which service routine has to be, which interrupt service routine or which interrupt handler has to be serviced. So that way it will come to know that, and the corresponding service routine will be executed, and with that whatever the device data whatever it is captured and also it will be transferred to CPU, or from that CPU it will be transferred to memory or whatever, so that can be done. So and again these details whatever I'm saying, the interrupt handling and all these details and all, it will be dealt more clearly in the your architecture part later on actually. And that way the devices we have seen, the hardware devices, how they interrupt the CPU and all to carry out their service whenever they have fulfilled the task and all. And the same way there is even the CPU will be like the user programs also will request the operating system service. So that will be done by using that known to be trap or exception, and this also known to be software interrupt. So the interrupts, whatever we just mentioned, like the devices, IO devices, and other things, and those are not to be hardware interrupts. It means that basically the hardware will interrupt the CPU to perform to carry out its service, right? So then the same way the user programs when they run, so they also need, yeah, right. Look something went wrong. Yeah. So yeah, can you able to see the slide? Hello?
Yes, yes.
Yes, sir.
Yeah, yeah, because I got some message like a warning, so that's the reason I stopped. Okay, so that way, even the user programs also need the intervention or need the operating system services in a different context. For example, when the user program is executing, if some error has occurred, as I mentioned, like division by zero or so on, or sometimes when the user program is executing, then the program needs some IO, for example. That means, suppose it needs some input from a keyboard or it needs some file to be like a RAID and something to be written into the file. So these are the various IO activities where the user program requires and all. So for doing all these things and also it requires the IO service is required and all. So, sorry, not IO, sorry, like interrupt, the OS service is required. The OS has to take care of that. So in that case also that means the current execution of the program will be stopped and the corresponding OS service will be done, carried out. So that way, in this case, these interrupts are not to be software generated interrupts because the user program, whatever the program that is executing, so that generates the interrupt. So these are sometimes also known to be trap or like exception and all exceptions, right? And so these are basically the software generated interrupts and all, either due to the like some malfunction is happening or some the error is going to happen while executing this particular program or the program itself needs some IO, right? So in that case also the current execution will be stopped and the corresponding like service routine OS service will be taken care. And yeah, as I mentioned that, yeah, this is we discussed. For example, if an interrupt occurs, then how does the CPU will know that actually which service routine need to be executed and all. So there are different ways. One is the using interrupt vector where the device will put its device number so that acts like interrupt vector. So with that, the corresponding interrupt service routine will be executed. And another way is that kind of a polling, as I mentioned that here. So whatever the devices were there, each device will contribute a single bit in the bit sequence, like in kind of a bitmap kind of a thing. So if none of the devices is interrupting, so in that case, all bits will be zero. And suppose if any device is interrupting, send the interrupt signal and all, for that particular interrupt, bit will be set to 1. So that way, the CPU, the other way of knowing the device which is interrupted, the CPU can just it will just scan that bitmap, the sequence of bits and all. So whichever the bit position is 1, it indicates that a particular device or the particular device is interrupted and also with that the corresponding service routine will be taken care. So that is not to be polling. It means that here the CPU after receiving the interrupt, then CPU is scan the bitmap. It just poll the bits of the sequence of bits, and then whichever the bit is 1, that indicates that the particular the device is interrupted and corresponding service routine will be taken care. It's not to be polling. So there are different ways and all, but just these are the some of them were just as a exemplary purpose we have just discussing here. And yeah, as I mentioned that after knowing that, then the separate segments of code will be determined and what action to be taken against to that particular interrupt. So that will be done based on that interrupt service routine. Yeah, the next thing is here is that actually this particular chart diagram indicates that actually how the CPU and the IO devices will execute with respect to the time. So here in this the plot at the in the upper portion, the top. So here you can able to see that this upper portion has the two levels. One is the here the level that means the upper one, that is the pulse, the positive amplitude. You can say the higher one, which indicates that the user process is executing. The user process is executing. And then here the pulse, the lower amplitude, or you can say that this negative one, you can say that if you assume that this is zero reference, this is negative one. So these pulse, these negative pulses, those things are indicating that the IO interrupt processing. That means when some device is sending a request, the interrupt request and all, then that interrupt service routine execution is indicated by this negative pulse, the duration of this negative pulse. And then once this interrupt service routine is over, and again the CPU will start executing the normal user process, like the next process, whatever. And then after some time, suppose when interrupt occurs again, it takes care of the interrupt service routine. So therefore, here in these two figures, the top figure, where the amplitude is fluctuating between the two levels, and in that the higher level indicates that the CPU is executing the user process, and the lower level indicates that the CPU is executing the IO some interrupt. Interrupting the executing interrupt is nothing but the in response to interrupt, the CPU execute the interrupt service routine. So that execution of interrupt service routine is indicated by to just to indicate that this particular time, the lower level. So then after execution of interrupt service routine, then the interrupt is processed, right? Then the CPU is free, then it will execute the user process. And then after some time again there is interrupt occurs, then it immediately takes care of the interrupt service routine. Then after finishing the interrupt service routine, then the CPU is free for execution of the normal user programs. So this timeline between these two levels, just to illustrate that one level is meant for indicating the user process execution, and the other level is indicating the like the OS routine or interrupt service execution and all. And coming to the bottom plot, where this also has the two levels, and here these two levels are indicated by, one level is indicated by idle, that means IO device, there is no activities taking place in the IO device, and the other level indicating that some data transfer is taking place. So in IO device, where the data transfer will takes place, because you have a device, and then for controlling the device, each device you have a device controller will be there. Suppose for example you have a keyboard. You have keyboard is the mechanical device, and then that device is connected to the device controller, and where the computer will interact with this device controller, right? So here in the IO device, the transferring of data, the data communication means from the device to the device controller. So here in this plot, actually here the level, the bottom level, indicating that the data transfer that is happening in the IO device, and the level, the upper level, or you can say that the higher level, indicating that there is no activity at all. Then the IO device is idle and all. IO device is idle. So that way, this particular plot indicate is fluctuating between the activity of IO device, and you can able to these vertical lines indicating that some event has occurred. Suppose the IO request has occurred, for example, the IO request has made. Then till that point, there is no IO activity at all. When IO request is made, then accordingly the as per the request, whether it's a read request or the write request, whatever. So the corresponding activity will takes place. Corresponding activity will takes place between the device and a device controller. And then once that activity is over, then it has to inform to the CPU. Then it has to inform to the CPU so that the CPU will take care of that. CPU will take care of that. Suppose, for example, you have a keyboard controller, for example. So the user program requires the input from the user and all. So that means there is IO request were made by the user program, right? And then the IO request is made at this point. Then it means that actually the OS will place the corresponding status information through the device driver into the device controller. Then the device controller will come to know that there is some data that is about to given the user will supply, and you need to capture that data, capture that particular keystroke or the character or whatever. So that way, here at this point of time, the IO request is made by the user program, and then subsequently the corresponding operating system routine or the device driver and all, it will place the desired control information into the device controller. So with that, the device controller will come to know that there will be some data that is available from the keyboard, and you need to capture that. So that is done by using here. That means IO request is made. Then afterwards, whatever the data transfer between the device to the controller, that takes place here. And then once the data transfer is over, that means once the data is captured, then the device control is ready. That means data is now available. So that will be informed to the CPU. How the transfer is done, that will be informed to the CPU. How? By using interrupt, by sending a signal to the CPU through interrupt pin at the interrupt pin. So that here the CPU will realize that the interrupt has occurred, right? Here the CPU at this instant the transfer is complete. Then immediately the device controller will send the interrupt. Will send the interrupt. So then that means this is the time instant at which the CPU has received the interrupt. So at that time the CPU may be executing a process, one of the instructions of the process. So let the CPU will complete that instruction, and after that the CPU will after that, the CPU will take care about that interrupt. That means whatever the interrupt that has arrived, it has to service that interrupt. So that will be carried out here after this one. So at this point of a time, the CPU may be in the execution of some instruction of the user program. So then after finishing that instruction, then the CPU will take care about the this particular interrupt. That means the corresponding interrupt service routine will be executed. That's what IO interrupt processing. It means that this one. So this negative small pulse. So during that time, the interrupt service routine will be executed, and then it means that with that the OS routine or the device driver will capture the input from the device controller. That means the CPU will get the input from a device controller, and then it has to pass on to a memory or whatever. So that will be done here during this interval. And once this interrupt service is over, then again the CPU will take care about the user programs. CPU will take care about the user programs and all. Take care about the user programs. And here again, and here once this transfer is complete, then the IO device will send the interrupt, and afterwards it is free. Afterwards it is free, like it is idle. Then upon again the next IO request, upon again IO request, then the IO device will perform the transferring, the IO transfer here. And then once the transfer is again done, so then again it will inform to the CPU. So when it requests the CPU, then the CPU will complete the current instruction, and then it starts execution of and then it starts the interrupt service routine will be carried out. So that way, by using this time chart, you can able to see that how the IO device and the CPU will coordinate to perform the IO activity and all. And then coming to this, yeah, when you perform this IO, there are different ways. Earlier, actually, if there is a non-interactive systems and all, and if the time is doesn't, if the multi-programming is not that much is not that much essential. So in that case, if IO starts, that means when IO request has come, when IO starts, then when a program needs IO, at that time then the CPU will then the user program starts waiting for IO. It means that control and then the program will be waiting for IO, and then the control returns to the user program only upon the IO completion. So till that point, the CPU will be keep on waiting for completion of IO, and whenever the IO completes, at that time the CPU will take care, and then the user program will be wherever it stopped, it starts running from that. This is like not in the context of multi-programming and all. In the case of multi-programming, where when the IO request occurs, and then when the IO starts, that means when the operating system takes care of that, and then the IO is initialized to the device controller and all. Then after that, immediately the control returns to the user program, and then the CPU will carry out the user program, some other user program, right? So that way, the for that actually we will make use of the system call. System call is nothing but the that means taking help of the OS routine, because the user program requires the IO, that is some input or some output, whatever. So in that case, it will be carried out by using the operating system. So therefore, the system call will be initiated, and then the system call will see that which IO is required, and based on that, the corresponding device table. Like for each device, it maintains the all devices, they maintain the kind of a table, device status table. So in that, with respect to that table, a particular user program is it requests the IO for a particular device, then it will add that to in that table, the corresponding interrupt request will be added to that. Suppose if the device is busy, already some requests are pending, then it has to be wait till that the preceding request has to be carried out. So that way you can able to the IO will be taken care. And there is another way of data transmission between the IO devices and the memory, and this is known to be direct memory access. So here, if you see that whatever we have seen, for example, if there is some high-speed IO devices where the data transmission or you need to have a data transfer instead of small amounts of data. Suppose if you need to have larger amounts of data that need to be transferred, for example. Suppose, for example, you have a user program where it requests some file, and where that file is there in the disk, for example, and the file size is also reasonably larger, and you need to bring that file from the disk to the memory. So in that case, actually, if you want to go by the normal way of data transfer, it means that the CPU has to take care about for every byte transfer or for every word transfer, the CPU has to intervene. That means using that the registers, the device control registers and all. First, it has to fetch to the CPU, then the CPU has to place it into the memory. So it means it takes a lot of time. And not only that, the CPU will waste, CPU will, for every byte transfer, for every word transfer, the CPU has to intervene. So that is fine for small amounts of data. Like for example, one word, two words are like a few bytes of data, it's fine. It can able to do that. But if you have larger amounts of data that need to be transferred, and for every axis, for every word axis, if you want the CPU intervention is required, it is very the CPU time will be wasted with this data transfer itself most of the times. So therefore, there is another way to handle that. It's known to be the direct memory access. So here the idea here is that if you want to transfer a large blocks of data from, for example, from a disk to a memory, for example, in the normal way is that actually from the disk, first of all, the disk controller will fetch the data from the disk, from whatever the file you are requested. So that has to be fetched by the disk controller from the disk, right? So disk is nothing but it's in like you have a hard disk where we have tracks, and then the sectors will be there. On that sectors, the data will be there in the form of a blocks. So first of all, you have to fetch the data from the disk controller. Then afterwards, from the disk controller, the CPU has to read, and again the CPU has to place into the memory location, specific memory location. So it needs a lot of time. That is, it takes care of like for every word transfer, you need to have minimum some 10 to 15 instructions need to be executed, and takes a lot of time. So to overcome that, you have another way of accessing a transferring a data between the like high-speed IO devices and memory. It's known to be direct memory access and all. So in this case, actually from the name itself, the CPU will not intervene for every byte transfer or for every word transfer and all. CPU will not intervene in this transmission for every word transfer and all. So for example, here the idea here is that very gross way. Suppose CPU requests a file transfer to be done from a disk to a memory in principle. So in that case, once the request is made to the device controller of the disk, then the device controller first it will fetch the data, whatever the 10 kilobytes or 20 kilobytes, whatever. So that data will be fetched and it will be kept in its local buffer. So once the data is ready, then the device controller will inform to the CPU, will inform to the CPU. Then the CPU will allow the bus or will allow for the data transmission from the device controller to the memory directly without intervention of the CPU and all, without the intervention of CPU. So at that time, actually, when the data is ready at a device controller, and if it is informed to the CPU, then the CPU can give access to the device controller to the bus. Then the device controller, by making use of the bus, it will directly transfer the data to the memory. That means for that, actually, it's not as simple as that. The CPU has to give the address locations from where the data has to be placed in the memory and all. So it has to give us some starting memory allocation, how much of data, how many bytes need to be transferred. So all the data, all the information will be provided to the both the device controller as well as the memory controller and all. Then with that, actually, then the device controller will perform the data transmission from the from the disk controller to the memory and all directly without intervention of CPU. And at that time, here the device may be informed to the CPU once per block. Once per block. Here the block may be like, for example, 4 kilobytes, for example, or maybe the 16 kilobytes. So that means till that block transfer, then the CPU will not be intervened. CPU will not be disturbed, right? Otherwise, in normal circumstances where the CPU will be intervened for every word transfer or for every whatever the size of the bus, if it is a 32-bit or 64-bit, like for every chunk of that word transfer, the CPU will be intervened and like CPU has to has to monitor and all. So here in this case, direct memory access and all, where the data will be transferred directly between the device controller and the memory directly without intervention of CPU, and the device controller will inform like a per block basis. So here the block size is much larger, much orders of larger magnitude compared to like a fundamental data transfer, like a byte or like a word transfer and all, right? So this is concept of the direct memory access and all. And now you can able to see this architecture where it supports the facility of direct memory access and the normal way of doing. And here you can see that here in this architecture, here this is the CPU, right? And this is your memory, main memory. And here these are the devices. Here this is one of the device, assuming that maybe a disk device or whatever. And here the CPU is executing a process, and here it's mentioned as a thread of execution. So don't worry about the terminology thread. Thread is nothing but a sequence of execution, a sequence of execution. So in a process, you may have the multiple sequence of executions which are independent, may happen. Like for example, you wrote a code, for example, you have your C program where it has some 4 or 5 C functions were there. And those C functions are such a way that those functions can be executed independently, without interfering to each other. So in that case, you can say that the program, if you have availability of multiple processes, you can able to run that program on a multiple process, even though it's a single program, single process, since there are like multiple sequence of executions are there which are independent. Like that means what I mean to say is that in a program, we have 4 functions are there, and all those functions are independent, assuming that they don't interfere. So in that case, you can start those functions, you can execute those 4 functions simultaneously. So that concept is known to be thread. So in that case, you can say that that particular process is having a 4 threads, 4 threads. So that means a sequence of execution, independent execution, is known to be thread and all. So anyway, we will discuss about these threads exclusively in one of the chapters and all. So there it will be more clearer to you what are the advantage of threads and other things and all. So it's basically thread of it's execution, like it's a process execution. And here in the process execution, and it may require the IO. So if it requires IO, first it will send the IO request. So the IO request means it will not directly contact the device and all. It will, when the IO request means it will just contact the OS, and the OS will intervene, and the OS will put the request to the device and all. And then the device, when that whatever the data is transfer is over, then the device will send the interrupt. Device will send the interrupt back to the CPU, and then the data transmission will take place. Here you can see the data will be, the arrow will be both sides. So here the arrow will be both sides. When the IO request is made, at that time whatever the input that has to be given to the device, that will be carried out by using OS, by using the device drivers in the OS. The device drivers, because the OS contains the device drivers. It's a software where the device driver will be specific to each of the device type, like the way the device controller are there. So similar to that, in the OS also it has a different types of device drivers are there, which used to manage the, which can be used to talk to the corresponding device controller. So when the IO request is made by the process, right, then immediately the OS will take over, and the OS, in that OS means the particular device driver will send that control information, whatever is required, to the particular device controller. So that way I can say that here the data, this towards the arrow towards this device is indicating that the OS will send the data to the device controller, right? And then upon that, then the device controller, based on the whatever the state, the information that is there, and with that actually either can read the data, it can take the input from the data from the keyboard or whatever the device and all. Then once that input is ready, the available at the device controller, then it will inform to the CPU using the interrupt. Inform to the CPU using the interrupt. And upon informing to the CPU, then the CPU will again run the OS routine, or the corresponding interrupt service routine. So when it runs the interrupt service routine, at that time, whatever the data that was there in the device controller, that will be read by the CPU. So that way you can say that the data will be back and forth, right? And the same way, yeah, this is for the normal way of IO transfer, like
Hello.
the interrupt driven IO transfer, right?
Hello.
Uh, Yeah, hello.
Yes, sir. Sir, I had a doubt that when the device is basically sending data to the CPU for execution, so does the operating system like switch to the kernel mode at that time?
Yeah, yeah. No, no. Whenever the operating system is running,
Yes.
right, it is in a kernel mode.
Okay.
Yeah. Whenever the whatever the operating system instruction, or operating system code, or operating system function is running, it's in the kernel mode.
Okay,
Okay.
sir.
So this is a normal IO transfer, right? And then just now I just mentioned that there is another way of IO transfer between the devices to the memory. So that is known to be DMA. So when if you want to transfer a large chunks of data between the device to the memory, for example, as I mentioned, like you need to transfer a file from a disk to hard disk to the memory. So in that case, based on the file size, it has a large amount of data need to be transferred. So in that case, it's better to use the DMA. You can use the DMA. That means direct memory access. So with the direct memory access, you can able to transfer from either side, from the memory, from a disk to the memory, or memory to the disk. If you want to write something into the disk, for example, you want to remove the file, for example, or otherwise this file you want to write something here and all in that file. So after writing that, this again the content has to be placed into the device also. So that way, the DMA can be done in the both the ways. You can read and write. So this is the direct memory access, right? And then here there's a cache. This will discuss a bit later. The cache is nothing but a small amount of buffer or memory, which is very fast, where that is the reason that it is attached to the CPU or like a part of the CPU also, where the CPU can able to access these memory locations very fast compared to accessing the main memory. It's like order of differences will be there. Suppose for accessing the main memory, if it takes about 100 nanoseconds, and for accessing the contents of the cache, it takes about order of nanosecond, or like 2-3 nanoseconds. So that's the difference between the access time of a cache versus access time of the main memory and all. So that way, nowadays, most of the processors, they have some cache memory, and where the instructions that are to be executed in a very short while, or in the future in a very so those instructions will be placed in the cache, and then the CPU, whatever the instructions required, first it will check with the cache, and if it is not there, then only it will go for the main memory. It will check for the main memory, access the main memory and all. So that way here, and again, as you know, that CPU will interact with the memory. So therefore, that there will be data movement between the memory and the CPU. So both the directions and all. Because CPU will take data from the memory, like it will fetch the instructions and the data also. And then at the same time, it will also write into the memory also results or whatever and all. So that way, this is the basic architecture of the way with respect to the data flow. Then coming to the storage structure. So far, we just discussed about the like the communication inside the computer between the I/O peripherals to the CPU and those the aspects. Now we'll just discuss about the different the storage structure, or like you say that different ways how the data or the programs and where they are stored and all. So you have the in the storage structure, there are different types of storage in at a different levels. We have seen already here in the previous diagram where we have already seen the storage at two levels. So one is at a main memory, like we can say that this is the memory where the CPU can have access, and then along with that there is another memory known to be cache memory, which is the size is small and the speed is the access time is very fast here, and the cost wise also it is expensive. So here you can able to see that there are two types of memory. One is the cache memory, and another one is the main memory and all. So here these two are differ, or the characteristics are different with respect to the speed and the size and so on. So likewise, you have for storing the data and all, you have the storage, the memory will be there at a multiple levels and all. So we'll see that. And the main memory is the one where the largest storage media, where the CPU can access directly. CPU can access directly the main memory and all can do that. And the main memory usually will do a random access. It means that random access means suppose the main memory size equals to, for example, you have about 12 GB, for example. So it means that 12 GB means there are about like in principle like 12 into 10 power 9 locations, memory locations, where each location holds a byte. So it means that in the random access means here for accessing any of the location, like in principle, it takes the time to access any memory location will be same. Will be same. It's not a sequential access. It's not a sequential access. Suppose if you take some other medium, suppose when you take a tape, for example, magnetic tape or some other thing, where the access is a sequential one. That means here you need to access the tape like sequentially so that you reach to the particular point where the file is available. But whereas here in case of main memory where the access is a random access, it means that so if you give a memory address, whether it may be at the lowermost address or the higher address or wherever, and it almost takes the same amount of time to reach to access that particular memory location. That's what I mean by the random access. And it's a volatile. It means that the contents of the memory are not will be off or will be lost when you remove the power or when there is no power at all. So it's what I mean by the volatile and all. That means the main memory, the contents will be lost when you switch off. And again, when you switched on, again it has to load from the like non-volatile memory, whatever is there behind that. So this is the characteristics. And the secondary storage, it means basically a hard disk in our perception, like extension to the main memory that provides a larger non-volatile storage capacity. So the hard disk where the contents are like permanent. Contents are permanent. Even though if you switch off also, the contents that will be there in the hard disk, they don't erase at all. They will be there. So that's what this is a non-volatile memory. And as all of us are familiar that the hard disk, the size of the secondary storage is much larger compared to the main memory and all. And then coming to the hard disk, the magnetic disk. Excuse me. Pratap. प्रताप I mean क्यों हाँ किसका Okay, okay, okay. Yeah. Yeah, I have, now हाँ अच्छा उसको सेंड कर दीजिए अच्छा हाँ अच्छा मैं बात करूँ मैं अभी क्लास में हूँ बाद में कर बात करूँगा हाँ थैंक यू ओके या So yeah, right. Coming to the magnetic disks, yeah, that's nothing but the hard disks, whatever we know that, and you know that in the hard disk, the way the characteristics of hard disk will be like it's like magnetic recording material will be coated, and there the data will be organized, will be in the form of like the self in the form of tracks and sectors. So on that, the data will be like stored and all in the form of a blocks of data, right? And the device controller will takes care of that. Device controller, that the disk controller, whatever is there, that determines the like logical interaction between the device and the computer. So actually, if you look at here this one, so therefore, if you see the disk and all, the nature of the disk will be different for storing the information and all. And if you see the some other device, for example, you can have semiconductor devices where the nature of storage, the main memory, for example, where the nature of storage, the way the information will be stored, that will be different. And for example, you have a mouse, for example, the way the information that is you can picked up from the mouse where the nature is different, and likewise keyboard. So that way, all these devices they have their different characteristics for acquiring the data. So therefore, you need to have specific device controller which hides the physical properties, the physical characteristics of the device and all. So that way, for a computer, all these device controller will give you a uniform interface where they can able to access directly to the all these devices and all. So that's the purpose of the device controller and all. And as you've seen that, as I mentioned, that the storage will be in the hierarchical way. We have already seen that the cache versus main memory and all. And this hierarchy depends upon these properties like speed, cost, and volatility. Like cost means the this one, the normal, the price, and speed is the access time, and volatility means the permanency of the contents and all. So these things will vary. Like as you go to the upper side, like towards if you want to have a very high speed memory and all, where the cost will be more and the volatility will not be there. And then if you come down at a bottom level where the speed will be less and it offers a very large storage and it offers a non-volatility. It means that the contents whatever is there, so that will be stable and it will be permanent, and the cost is also a bit reasonable. So that way these three factors varies with respect to the hierarchy. We'll see that. And caching, we have already mentioned the purpose of caching and all, copying the information into faster storage system. For example, a main memory can be viewed as a cache to the secondary storage, obvious, right? The main memory can be viewed as a cache to the secondary storage, because you see the secondary storage, the volume of, or you can say that the size of the secondary storage will be in the form of terabytes, whereas the main memory, its order is in terms of like gigabytes and all. And with respect to speeds also, like for a disk access and all, you have the speed will be in terms of milliseconds, for example. Whereas if you want to access the main memory, the speed will be in the terms of like tens or hundreds of nanoseconds. So that way you can use the hierarchy. You can see here. So this is the hierarchy of the storage, where it starts from the magnetic tapes to at the bottom side to the registers. That is, registers are nothing but these are the like the storage elements that are within the CPU, right? Within the CPU. And so here from this hierarchy, you can come to know that the registers are very fast. That means CPU can able to access the registers at highest speed, at very fast, with very low access time and all. Then the cache, then the main memory, then the other things like electronic disk, magnetic disk, and so on. So this is the way the memory hierarchy will be there. And then if you look at that, actually the properties, whatever I just mentioned, the speed, cost, access time, and the like volatility and other things and all. So they follow based on this hierarchy and all, right? Yeah, as we have already mentioned that the caching and all, it's like, yeah, this is just very intuitive. Like you can use the caching at different levels and all, as I mentioned. Like you can say that the cache that is there within the processor and the main memory. So with respect to main memory, that becomes a cache, and the main memory happens to be cache for the secondary memory. Likewise, you can have different levels. The storage device, the storage system that is preceding to that happens to be cached to the system and all. So that way you can view that, and the information that is copied from a slower to the faster storage temporarily. And then the faster storage, the basic principle is that if you want to access the data, the CPU will first check the fastest device, the place, storage place, and then afterwards, if it is not there, then it will go to the next hierarchy, and that way, that is the way the data access will be done. And then, since the cache is a smaller one, then it has certain issues and all. Like there will be trade-off between the size of the cache and the information that to be stored and all. Like so that way, the size of the cache, and then since the cache is a limited size, and to feed the information from the main memory to the cache, or like the preceding storage to the cache and all. So there will be certain policies will be there, like what contents to be placed and which to be removed, for example. So all these things are there. It has its own policies and all, right? So this is about the caching. So it's a very generic one, the principle of caching and all. And you will study these things more detailed way in the computer architecture and all. So where you study that actually what the cache, how the cache is organized, and how the cache replacement policy. That means the information content actually, how the which data to be placed, which has to be removed. So all these things will be done by the mostly it is done by the hardware actually. So because the access time should be faster. So that way you can see the more details in your architecture part, right? Okay, so yeah, now let's take a break for 5 minutes. Okay, and after that we'll continue the lecture and all. So please take a break and we'll continue. And again, I will stop at 11:40. Then you can start the quiz at 11:45. Okay, so let's take a break and then we'll come back. Yeah, let me stop the recording now and then again I will start later.